We're not quite finished with our discussion about dielectrics. We finished last time talking about how we can improve the performance of a capacitor as a charge and energy storage device. Now we arrived at this final formula for capacitance. It turns out that we can improve the capacitance significantly by putting in a dielectric, an insulating material, kind of the filling of the sandwich, for the capacitor being the bread, okay? So, kappa is the dielectric constant of material, and if that's 2 or 3 or 1,000, you get that many factor times more the capacitance. Remember what ultimately, the mechanism by which it does that is that if you have charge on the plates, like so, then inserting that material will cause the insulator inside to charge polarize. It's going to suppress the electric field and therefore voltage. And ultimately, that means that we can put more charge on there for a given charging battery. Okay? So that's the general gist of how that worked. And then we, of course, for a parallel plate capacitor, we can, of course, put in what is it that determines the capacitance in the first place. We learned that the area, the plate area, the area of each plate and the plate separation determine the kind of baseline capacitance before you throw in the filling, throw in the dielectric. And so what I wanted to do today was carefully look at each of these terms. There's 3 active ingredients, kappa, A, and D. Remember, epsilon is a constant, okay? So you have 3 different options to improve the capacitance, okay? The first of which is the dielectric. So we just talked about that. If you can find a better dielectric material, then you can get the capacitance to be better. So for instance, if you were able to find a material where, say, kappa is 10, that means that it can suppress the voltage and electric field by a factor of 10, so it's 1/10 its previous value, and that's great. Here you're ultimately limited by just materials that you can find. So, as you can probably guess, there's a certain upper limit if you just grab various insulators from nature and just throw them in, you try them out, see what they do. And if you don't like those, then you can imagine human beings have gotten around to tinkering and synthesizing materials specifically for this purpose. And of course, the larger kappa they can get, the better, right? So this is limited by materials. So you have to be able to find something that has this particular property or manufacture it. If we wanted to make the capacitance better, what should we do to the plate areas? We should make them bigger, okay? So that's another way to improve the capacitance. I guess I should put this over here because these are all things that are improving the capacitance. So here, you're limited by materials. Might there be a downside to making the area very big? What's the downside to that?
Too big to fit on a circuit board.
Too big, yeah. What do you want to be carrying around with both hands? Okay. So there's a certain size limitation. So the size limitations. Now, I'll tell you there's a trick that they sometimes use in capacitors to fit a very large amount of area into a small volume. Okay? So what they do is that they are not really parallel plates. One looks like this. This is a more advanced capacitor where the plates aren't symmetric, but the other one is like this. The surface area is tremendous, but they also pack it into a very small volume, right? There's lots of crinkles and folds. If you actually pulled it out straight, it would be a massive area, but it's crinkled into a very small space. These are your electrolytic capacitors. And this, with recent technology, has enabled you to have a 1 farad capacitor, which would normally be the size of a football field, and allow you to hold it in your hand. Okay? So a tremendous amount of area in a small volume. Now obviously that's a little bit beyond the scope of the course because the plates aren't symmetric. Occasionally we'll have you use an electrolytic capacitor in lab, and one of the things in the instructions is always make sure you connect it the right way, because the two plates aren't exactly the same, and which one goes to the higher voltage and which one goes to the lower matters. Okay. There's something you can do with area. Let's take a look at the final factor. Actually, are there any questions before I do that? Okay, so let's take a look at D. What should we do with the plate separation D to make the capacitor better? Decrease it. Now that one seems like a win-win. I mean, we make the capacitor smaller and we make it better, right? Bring the plates closer together and it's better. What's the downside to that? Well, as you can guess, everything has a downside. So that's when we get to something called dielectric breakdown. So, let me remind you of the relationship between E, the electric field, voltage, and plate separation. It looks like this. Now, in our previous discussion from last lecture, we had D as being fixed, and so therefore we were looking at the electric field and voltage difference going together. So that's what allowed us to say, oh, if the insulating material, the dielectric, if it suppresses, it partially shields the electric field, then the voltage difference will also go down, right? But now, we're talking about messing around with D. So let's say we have V fixed, right? So let's say we have, for instance, V across the capacitor is fixed by a battery, right? But if we decrease D, what's going to happen to the electric field? It's going to increase. So the idea there is that the battery holds the voltage difference across the plates fixed, but if we bring these plates really close together, it's a precipitous drop of voltage from one place to another in a very short distance, right? We might have a 9-volt drop from here to here, very small distance, and of course, one of the things you hopefully learned in the electric field mapping lab is that if you have precipitous plunges in voltage, that means a very strong electric field. So, what's the big deal about the electric field being strong? Well, there's such a thing as too strong, okay? So, this is the time where we realize once again that the distinction between insulator and conductor is a fluid, continuous thing. Remember that these guys are just atoms that have been rotated because of the influence of the plates, right? In fact, rotated isn't really necessarily the best way to describe it. If you think of it like this, what is an atom normally? It's a positively charged nucleus surrounded pretty much symmetrically by electrons, right? Now you guys may know from chemistry that there are such a thing as polar molecules, right? Where the plus and minus aren't exactly concurrent. These things have a permanent dipole, right? They can be approximated as a plus or minus, kind of separate. But what we're doing here is when we apply the external field from the plates, E external, what we're doing is even if it doesn't have a permanent dipole moment, or permanent dipole, we are pulling the charges to one side. Not entirely, but of course on average, right, like that. So the negatives go upstream and the positives go downstream. This is what's called an induced dipole. You guys talk about this in chemistry? Okay, good. So, here's what happens though. A little bit of this is good, because that's what gets you your partial shielding, right? A little bit of this means that now there's a plus over here and a minus over here, so there's your E induced, right? And that's what gets you your partial shielding. Partial shield. But there is going to be a point where these minuses not only get pulled upstream, they literally get yanked off of the thing, right? So we like our molecules to be stretchy, right? That's what gets us the partial shielding. But everything that stretches, you stretch it too far, it breaks, right? So that's what happens if you go too far. If this external electric field is too strong, these minuses don't just get pulled up here, they get pulled off, okay? If E external is too strong, it'll literally break that stuff apart. And suddenly you have a bunch of free electrons where there were no free electrons. You've turned bound electrons, electrons that belong to that nucleus, into up for grabs, right? And that's what we have is called dielectric breakdown. So dielectric breakdown is when the external electric field is so strong that it does not just charge polarize. So it does not only charge polarize and therefore partial shield, but it actually breaks the atoms and molecules in the dielectric or the insulator. So that's bad news, right? Because if the whole goal of the dielectric is to provide shielding, you've just broken those things, and now you have mobile charge, so minuses that are sitting next to the positive plate are literally going to be pulled off onto the positive plate and neutralize that charge, and vice versa with the other plate. So if you literally scissor, let's go like this, we scissor these, we kill these, then what we have is that there's going to be charge cancellation. And you've defeated the whole purpose of the capacitor. So, how do we quantify this? Well, every material, every dielectric material, it not only has a dielectric constant, which tells you about its ability to partial shield, it also has an upper limit. It has a dielectric strength. That is simply an electric field that is so strong that if you exceed that, you'll tear it apart, okay? So, for every material, it has two values. It has a kappa, which is telling you about its ability to partial shield. If you haven't, don't tax it too much. And it also has a dielectric strength, or dielectric breakdown. It's just an electric field. So if you go on to the equation sheet, if you look in the bottom corner there at page 1, you'll see a list of materials and you'll have two values for each one. The kappa value, which tells you about how well it functions as a dielectric, and the dielectric strength, which is the maximum electric field. If you exceed it, you will literally kill the ability of its partial shielding. You'll tear it apart and it will not be able to act as you want it to anymore. And of course, that's what we're in danger of if we make the plate separation too small. The electric field is going to go too large and exceed the dielectric strength. Okay? So if we go over here and we talk about what's the catch, Kappa is limited by the materials, but this is also limited by the materials. So what you want to do is not go too small, such that the dielectric strength is exceeded. And you will find that when you buy capacitors at the store, they will tell you, do not try to plug this in above a certain voltage, because of course if you do that, you will zap the dielectric. And usually it's a permanent thing. Okay, this is not something, or oops, I'm going to unplug it, and I'm going to use it again. This is a permanent tearing apart of the material, and you can't put it back together. Okay, so it's time to put in a new capacitor. So this is oftentimes, one of the things that goes wrong in electric circuits that requires repair is if you blow out a capacitor like this, you literally exceed the dielectric strength. Then there's a permanent damage to that material. You need to put in a new one. Okay. So to give you an example, one of the most common types of dielectric to look at is air, right? For air, just to give you an idea, the dielectric strength is 3 times 10 to the 6 newtons per coulomb, or of course, we learned equivalently, volts per meter. So you might see this written as 3 megavolts per meter, right? Mega is 10 to the 6th. If you apply an electric field greater than that to air, you'll tear it apart. So one of the problems on your homework asks you to evaluate the dielectric breakdown in 2 circumstances, 2 very common everyday circumstances. One of which is walking up to a doorknob on a dry day and zzz, your finger zaps the doorknob. So that's dielectric breakdown. Your finger is serving as one plate of the capacitor, the doorknob as the other. And when the gap gets close enough, right, if you shrink the distance close enough, the electric field between you and your finger and the doorknob, it will exceed the dielectric strength of air, and you'll zap the air. You'll have a little spark that jumps. Okay? This is also what lightning is. Lightning is dielectric breakdown of air. So obviously it's happening over a much further distance. Okay? And that's, of course, because the charge involved in whatnot is a lot more. Okay? So chances are you do not have enough charge on your finger to jump from here to the next building, right? But you can jump a few millimeters from your finger to the doorknob, right? So I actually have you compute the exact numbers involved, and you'll find out they're both the same thing. They're both the dielectric breakdown of air, but why is it that you don't want to be hit by lightning, but you can easily withstand a shock from a little zap to the finger, okay? So that's dielectric breakdown. Are there any questions on that? Yeah.
So when there's dielectric breakdown, is there electric current going from one plate to the other plate?
That's exactly right, because
Okay.
anytime you have the mobility of charge, we can call that a current, right? Are there any other questions? Okay, so the final order of business on homework 4 is something I've been hinting at for some time, which is let's put caps in series and parallel. Okay, so there are certain components just like anything, so we should be prepared for having more than one of them in a circuit. So let's do caps in series and parallel. And I'm going to start with the parallel one, just because it's the easier one, and I'll do the series second. So here's my battery, and I'm going to charge not one but 2 capacitors. C1 and C2. Now, I could certainly put a resistor in the way and have it charge exponentially, take till infinity to fill forever, but we already talked about that. Let's just have no resistance in the way so these caps are basically going to charge instantaneously. Okay. And I purposely, if that is not a mistake, I have had the plates of capacitor 2 seemingly pretty stretched out there. And that's because I want to have some visual representation of why, of the fact that the capacitor 2 is the larger one. Okay? Now, I could, of course, have a larger capacitance value for many different reasons. It could have a better dielectric, or the plates could be closer together. But I'm choosing to represent it by the fact that the plates have a larger area. Okay? So let's think about what happens here. If you connect this up, then the battery immediately wants to turn the top section into an equipotential with the positive terminal, the high voltage terminal. And of course, the way it can do that is by putting charge on these guys. So plus charge is going to flow onto here and onto here. So, like so. And the battery really acting as like a pump will, of course, also create a negative charge on the other one. Okay? So that's what we have. And of course, by very nature of parallel, this is true whether the resistors or caps, the voltage drop across both is the same, right? So let's start another kind of master chart here, series and parallel. So we had a kind of a long column here for resistors in series and parallel. Let's make a similar chart with caps. And with parallel, which is what we're starting with, is of course the voltage is the same across each one. Okay? So this is not new. This is the same whether they're resistors or caps. Okay? In fact, both of them are going to charge up to the battery voltage, right? That's all that's going to happen here. But let's, and we can say that V1 equals V2 is just the battery voltage, okay? That's when the charging process is done. When both of these caps have the same voltage drop as the battery they're connected to. So, let's talk about charge though. Q equals CV. I'm just inverting the capacitance formula to solve for Q. And I've just said that the voltage is the same, but if the capacitances are not, will the charge be? No. In fact, which capacitor will get more charge? The second one, exactly. So for the same voltage drop, if it's a better capacitor, it'll get more charge. So, we're adding another column here. Voltage is the same, but the charge is not. Charge is not. The larger capacitor gets more charge. If you take two capacitors and apply the same voltage drops, that's the same amount of effort to charge them both, but one's better. One has a larger capacitance. It'll store more charge. Okay? In fact, if you wanted to calculate those, of course, you go Q1 equals C1 times the voltage, which is just the battery EMF, and same thing here with the other one. And I guess I've already drawn it that way, but I should probably emphasize this. So this capacitor has much more charge on it. Looks like that. So now you can probably guess what's coming. If we wanted to combine these two capacitors and think of them as one, how would we do that? Well, we have once again our equivalent circuit. So if we were going to imagine both capacitors as a single capacitance, an equivalent capacitance, what would we do? Of course here, this is plus Q total, and this is minus Q total. So if we think of the whole bank of capacitors as one, then there's a certain total amount of charge separation, plus and minus. And we can, of course, use good old Q equals CV for the entire equivalent circuit as well. Q total equals C equivalent times, and then here, of course, the voltage drop is just the battery EMF. So, now, how much charge have we really separated? Well, let me point out that if I have Q1 over here and Q2 over here, I've actually separated just the sum, right? So the amount of charge I've been able to separate on each plate is just Q1 and Q2 add together. If you want to think about this in terms of conceptual, just conceptually, you can think of these two storage devices, it's almost like this, right? It's almost like if you have two parking lots for charge, it's like two parking lots means one big parking lot, right? It just happens to have two entrances, right? And it also happens to, of course, have some kind of barrier between them, right? It's like sometimes you see, right, there's like what seems like a big parking lot, it's got two entrances, but then when you're driving around you realize, oh, I can't actually get from this part to this other part. But it still effectively serves as one big parking lot, right? So that's what we have. So what we're expecting here is that if you have two capacitors in parallel, that actually should be a larger capacitance overall. So what we expect is, of course, that C equivalent should be larger than the individual, I guess I've just been calling them C sub I. We expect that the capacitance overall should be greater than either one, because we've been able to separate the charge on both. And in fact, let's go ahead and plug in our equations here. This is C equivalent times the EMF. This is C1 times the EMF. This is C2 times the EMF. We plug in what we have from here and from here. We cancel that off and we find, indeed, when you combine capacitors in parallel, you get that the equivalent capacitance is just the sum of the individuals. So now we have our addition rule. So we have that C equivalent for capacitors in parallel is just the sum of the individual ones. Did I use I or N before? I can't remember what subscript I used. Did I use?
You think you use N.
N, okay, let's do N, sorry. C sub N, okay. You just add them up. And of course, one of the consequences of this simple addition is that if you have a bunch of identical ones, if they're identical, you just multiply the number you have times the capacitance of 1. That's not nanocoulombs. I don't know how to make that clear. N times C. Okay? So if you happen to have 10 1-farad capacitors placed in parallel, that's like a 10-farad capacitor acting as, so you have basically a bank of capacitors all working together, right? Okay? Now, one of the things you might notice right away is, wait, so you just do a straight addition of the capacitors when they're in parallel? That's what we did for resistors, but when they were placed in series, right? It's going to turn out that the addition rules are actually flipped. So I'll just spoil that punchline right now. I'll show you, of course, when we get to series, but for the 1 over rule, that used to be for parallel resistors, now it's for series capacitors. I'll prove that to you later, but I just want to point out at this point that the rules are reversed. Oh, I forgot to mention also here, to add to my chart, of course, when you're adding them in straight addition, the result is greater than any individual one. And one of the things we discovered over here was that, of course, the result is less than any individual one. Those are just consequences of those addition rules being what they are. And in fact, adding over here, when we have them identical, you divide by the number you have, right? Instead of multiplying. Sorry, this is getting a little crowded. Let me move it a little bit over here. This is also on your summary sheet. So the rules are reversed. I'll talk a little bit about why that is. There's a way to think of this why they're reversed. But for right now, before I move into the series, I of course have to talk about energy storage. Okay? Are there any questions before I do the potential energy? Okay, so let's knock out the potential energy. Let's go over here. So I have three different forms of the potential energy law. And here I can finally kind of show you why is it that we might prefer this one for parallel capacitors. Well, it's for the same reason I preferred the similar formula for parallel resistors, is because V is very hard to mess up, right? You can't mess up V because V is the same for everybody. Are the other ones wrong? No, but you have to really watch it because Q is not the same for both of them. This one's the easier one to avoid messing up. And in fact, it tells us that if V is the same for everybody, if C is larger, what does that mean about the potential energy? It's larger as well. So C is larger, PE is larger. So we can add that over here. The larger capacitors will hold more energy. So if you have a bunch of capacitors in parallel, they don't all hold the same amount of energy. The larger ones hold more. Now, to think about this conceptually, I do want to refer back to this one, this original one. And the reason I like that original one is because it tells me the two ingredients that go into how much energy is stored. Q is how many charge carriers you have on there. And V, remember what V is, volts, energy per charge. So it tells us how many total charges are on there and how much energy do they each carry, right? So if we go here, we know it's the same energy per charge, right? So we know that when the two capacitors are in parallel, the exact same amount of voltage is applied across both of them, so it's the same amount of energy contained per unit charge. So why is it that the bigger capacitor has more energy on it? It has more charge. It has more total charge. So if you have more total charge, then you will have more total energy. That's why. So if you went to any one individual charge here, let's say comparing this plus charge with this plus charge, they have the exact same amount of energy. Because the energy per charge is the same. The difference is that this one doesn't have as many of those, and this one has many more. Okay? That's why the larger capacitor stores more energy. Okay? So if I wanted to add in here, why does the larger capacitor have more energy? It has more charges. That's why. Not because it has a higher voltage, but because it has more charge. Okay? Have any questions on this? Yeah?
So that, as C goes up, E goes up, that doesn't really hold true for the next, the equation on the right there, does it?
Which one? This one?
No, sorry, your set of 3 up there.
This one?
As C goes up, wouldn't PE go down on that?
Well, so this is the one that would be the worst to look at because both Q and C are changing, right?
Okay.
Right. So the larger capacitor has more charge and more capacitance. So if the numerator is increasing and the denominator is increasing,
But the numerator squared.
that's exactly right. So the numerator matters more. But again, you've picked the very hardest one to look at to see why the potential energy increases. That's why this one's easy, right? It holds something fixed. In parallel, V is fixed, so you only have one ingredient left. So you can easily see if C goes up, PE goes up. So always want to make your life easier instead of harder, right? But it is consistent, of course, across all 3. Okay, any questions before I move on to the series one? We'll work the series the same way. Okay, so let's do it. I'll leave some of the same stuff up so I can refer to it later. This is just generic potential energy stuff. Let's do caps and series. So now I'll take the exact same 2 capacitors, attach them to the same exact battery, but do them in different ways. I'll connect them in a row, like that. So, let's track what happens. Well, charge is going to flow off here, accumulate on here, and of course the electric field generated by those will generate that plus charges get pushed off of that plate, leaving a minus charge behind. Those plus charges that get repelled off that plate don't have far to go because they now accumulate over here. And once they accumulate over there, they of course push positive charge off there. It's kind of like a relay race, okay? So this relay race, if you think about just one capacitor, right, it's just one plus charge and then one plus arrives at the plus plate and then one plus charge gets pushed off the negative. This is a relay race though with a middle leg. So there is a sloshed movement of charge here where neither the original destination or the original source nor the final destination is not a battery terminal, okay? Now, this is where it's probably easiest to prove to you that the charge here is the same. So this is plus Q, this is minus Q, this is plus Q, this is minus Q. So I have a couple different reasonings for that. Well, first of all, if you didn't have that, you would have charge accumulating somewhere, okay? No, that's not a good way to put it. Let me put it another way. Look at this middle section. This middle section is 2 disconnected plates that aren't touching anything. They're just connected to each other by a wire. If this was neutral to begin with, how is it going to not be neutral at the end? So the plus charge just flows from here and ends up over here. But this section overall has to be neutral. In fact, you can think of this as just basically charge polarizing in the electric field of the outside. So it looks a little funky, but might as well be this. middle section is just charge polarizing in the electric field of the outsides. Okay? It just, instead of looking like a sphere like we normally draw it, it looks like two metal plates with a wire attached. Okay? So this is a relay race, charge being the same. So we put the same amount of charge on each plate. However, just like with resistors, that does not mean the voltage is the same, right? So with resistors, we talked about the current being the same, right? The current is the same through every element, because there's no forks. You have to go through each one. Well now, instead of current, we're talking about what current accumulates, which is charge. So there's charge is the same. And we also learned that the voltage drops were not the same, right? In series, the voltage drops were not the same. Let's find out what happens. The only thing we know for sure is that the sum of the two has to be the battery voltage, but they are not necessarily equal. If we go back and we look at our formula, let's invert our definition of capacitance, V equals Q over C. If they have the same charge, but one of the capacitance is larger, what does that mean about the voltage across that capacitor? Smaller. Interesting. We find that the voltage is not the same. We find that these smaller capacitors have the larger voltage drops. So that may seem counterintuitive, but let me try to explain to you why that is. This is a small capacitor that has a larger voltage drop, and this is the larger one, and it has less. So let's think about this. This is a small capacitor. It's not as good of a storage device. And you've crammed a bunch of charge into a very bad small holding space, right? You put them in close together. That means that you're going to have a larger voltage drop between one plate and the other. Over here, they're the same amount of charge is lounging luxuriously on have all the room in the world, right? And so there's not going to be as big of a voltage drop over there. Think of it like you have to work harder to get that charge onto this plate, this capacitor, than this one, right? It's going to take more effort, right, to get it onto here, the small space, and less effort to get it onto this big, large space, okay? Does that make sense? So the bottlenecks in this case are the small capacitors, okay? So I used this terminology before for the series circuit, right? Because the thing in a series circuit is that you have to, everything has to be in the chain. Everything's in the chain. And so the bottleneck is the small capacitor. The small capacitor is the hard thing to store charge on. It's not as good of a storage device. So let's figure out what's the equivalent capacitance. This is plus Q total minus Q total. This is C equivalent. And once again, we can apply our equation for the equivalent as a whole. So how much charge have we really separated, plus Q total and minus Q total? Well, we've got plus Q on one end, we've got minus Q on the other end. And if we pulled out this segment in between, we'd have a neutral hunk of stuff, okay? So really, the charge separation we've been able to achieve is plus Q at the beginning, minus Q at the end, and it kind of flip-flops in between, but we haven't really gotten more storage ability, right? Again, if I took this middle segment out, right? I'd have a neutral hunk of stuff. So basically, Q total is Q. Q total and Q1 and Q2 are all the same thing. The amount of charge I've been able to separate overall from beginning to end is the same amount of charge that both capacitors individually have been able to separate. So let's see what happens there. Let me take this thing here and I'll plug in for that. I'll plug in that EMF is Q total over C equivalent. And here I'll plug it in for the individual resistors. And then I cancel the Q's because they all separate the same amount of charge. And what do I get? I get my 1 over rule, right? So if you plug in capacitors in series, you actually get a worse storage device. How can you think of that conceptually? Well, you aren't able to separate any more charge than if you connected overall as they do individually, and of course you have to split the voltage drop between them, so you don't put as much effort into either one as you would if they were both connected across the battery terminals. You might question, why would you want a capacitance that was low? Well, you of course want to always be able to tune in whatever capacitance you want based on the capacitors you have. So if you want a certain capacitance and you only have capacitors that are bigger than that, you can put them in a series to bring the value down. Okay? Are there any questions before I talk about energy? Okay, so let's talk about energy. I'll go over here. This is the one I'd probably want to use for series, right? And the reason I want to use that for series is not because the other ones are wrong, but because this one's the easiest to tell what happens, Q being fixed. Q is the same for both capacitors, and so I can tell here that the larger capacitors will store less or more energy. Less energy. So let's put that over here. Actually, let me put it as the smaller capacitors store more energy. And once again, that's the easiest one to see it because it doesn't have, it just has Q is fixed, so I can see the direct link between capacitance and potential energy. But I again want to go back to this to try to understand conceptually why. So we know in this case Q is the same number of charges on each one. So now the reason why one stores more than the other is not because of total number of charge carriers, it's because of the voltage. Okay? If you have more energy per charge, okay, so same number of charges, but more energy per charge, what does that mean about the potential energy? So it's more. So if we look at our two capacitors, which again I unfortunately erased here to try to make a point, we've taken the same amount of charge and crammed it into very close quarters on a smaller capacitor, and there's a lot of energy when you put charges very close together. So that's why that one stores more energy. The smaller cap, because it's got all that, all of that charge plugged in or stuffed in very close proximity, that's why it stores more energy than the one where the charges are just luxuriously hanging out. So here, this one is because it has more voltage drop. So more energy per charge. The number of charges on each capacitor is the same. It's about, are they crammed into close proximity or are they luxuriously hanging out away from each other? Okay. Okay. So now what I want to do is I want to show you that, and then to the extent that this is helpful, that there's a huge analogy between resistors and capacitors. I've already hinted at it, but I want to expound on that, okay? So we mentioned that in series, the bottleneck is where all the action is, right? The smaller capacitors, that's like the bottleneck, the bad storage devices. They get more voltage drop, they have more energy stored. The bad capacitors, right? Let me point out that when we were talking about bottlenecks before, what's the bottleneck in a series resistor chain? So which resistor is the one that gets the biggest, all the stuff? Is it the big resistor or the small resistor? It's the big resistor, right? We learned that the bottlenecks were the large resistors. They got the most voltage drop and dissipated the most power, right? That's where most of the action was. The large resistors, you have to pay them the most attention, right? They got the most voltage drop, they got the most power dissipated. Now we have that the small capacitor is acting the same way, right? That's the bottleneck. The small capacitor in here is going to get the larger voltage drop and the most energy stored. Okay? That's the bottleneck idea, right? That's where all the action is. In a series circuit, the big thing in the chain, the thing that is the biggest annoyance or whatever is going to get the most attention. The large resistors and the small capacitors, right? The small capacitors are more difficult to charge, right? They're more difficult to contend with, just like large resistors, right? Let's go to the parallel side. Remember, in series, you have to deal with everything because everything's in a row. But in parallel, you have choices, right? You don't have to contend with everything. You have to pick a path, right? So in a parallel resistors, you pick one branch to flow through, right? No charge carrier will flow through all of them, right? So now we talked about this as the sideshow, right? I'm not going to have any room here. Let me try to sneak it in here. So we talked about the sideshow. Okay. So we talked about this idea that now the action is at the small resistors, right? We found that these small resistors was where most of the current went, right? And also had the most power dissipated as well. It's the large resistors that are the kind of afterthought, right? The sideshow. So it's the large resistors. I guess, which way do I want to do it? I guess I'll deal with the small resistors. They get the more current or less current? More current and more power dissipated, because that's where all the action is. So they're not the sideshow. The sideshow is the large resistors. Sorry.
I thought the power went up with the larger resistor.
That's for when they're in series. In parallel, it's the other way.
Okay.
So the large resistors are now the sideshow, and the most action is at the small resistors, right? So the small resistors in parallel get the most current because it's the easy way, and they also dissipate the most power. Well, same deal, okay? So the small resistor is easier here. The large capacitor is easier, right? The large capacitor is easier to store charge. So what do we see? The larger capacitor stores more charge and stores more energy. So the common theme, right? The common theme is the fact that when you're in series and you have to contend with everybody, the most action is the difficult, the bottlenecks, right? The larger resistors and the smaller capacitors are the difficult things. They get the most attention because you have to pay attention to everything. When you get to parallel and you have choices, then all the action's at the easiest way, right? The smaller resistors and the larger capacitors get the most action, and the difficult stuff, the difficult branches, the higher resistors and the lower capacitors are the sideshow, okay? So it seems like everything that happens with a resistor, a big resistor, happens with a small capacitor. It's almost like they're inversely related. Now, of course, they're apples and oranges, but let me show you something. Ohm's law, V equals IR. Okay? Let me write for capacitor, Q, and let me write it like this. So that's how resistance is defined by Ohm's law and how capacitance is defined. Look at this. V, right? Voltage drop across them. Current, which is the charge that flows through them, and then Q, of course, is just the charge that accumulates. So we call it Q instead of I, right? Look at the rest of it. R is like 1 over C, right? And that is exactly why large resistances are like small capacitors, right? Makes it so large resistor, I don't know what the analogy symbol is. R is like 1 over C. Does that seem right? It's been a while since I took the SATs. Okay? So that's why they seem to be kind of flipped like that. The more difficult things are large resistors and small capacitors. And because of this relationship in the equations, it's no wonder that the addition rules got flipped, right? That's exactly why they got flipped. So remember, the straight addition, right, just adding the values, that works for series resistors and parallel capacitors. The 1 over rule, that works for parallel resistors and series capacitors, okay? So hopefully this gives you a kind of a nice way to see that there's an overarching behavior here between resistors and capacitors. If you're solid on series and parallel resistors, this isn't really that much different, okay? The key is just to remember that as goes a large resistor, so goes a small capacitor. And then the rest of it is just details. Instead of talking about current, we talk about the accumulation of current, which is charge. And instead of talking about power dissipated, which is energy being sent to the environment, we talk about PE, which is energy stored. Okay, so that's all your analogies. So instead of I, we talk about Q. Instead of talking about P, we talk about PE. Okay, so this right here will basically allow you to convert all your intuition about resistors into intuition about capacitors. Okay. Are there any questions on that? Yeah.
So you have, for parallel, the large resistors is shown as sideshow, so small resistors are then bottlenecks in parallel? Is that what that is?
Well, the bottleneck and sideshow are kind of like, so in series, when you have to contend with everything, then something has to be paid more attention to. So there is no sideshow in series, right? Because you have to go through everything. So it doesn't really make sense. So the bottleneck terminology really only makes sense for series. And likewise over here, a sideshow implies that you have choices and one thing is less important or less paid attention to than another choice. But a sideshow doesn't make sense in series because you have to go through everything, right? So you can't really take the bottleneck and sideshow and you cross your streams, right? Bottleneck is really only for series and sideshow is really only for parallel. Does that answer your question? Okay. Any other questions? Okay, so this, if you want to make a note of it, closes out your homework number 4. And it also does close out, for at least for the time being, our unit on electricity. We're going to be moving forward now into magnetism. We're going to find that later on that there's a strong connection between magnetism and electricity, so we're not done with this, but for the time being it seems like we're going to completely change gears